So radioactive isotopes are going to go through a type of radioactive decay, and there are different types of radioactive particles that can be given off. We have our alpha particle, which we use the lowercase Greek alpha. It is the same as a helium nucleus. So this is the symbol that we would use in a nuclear equation. We have beta particles, which are essentially electrons, but high-speed electrons. We have gamma rays, which are electromagnetic radiation. Notice no mass or atomic number to use in an equation. And we have positron, which look at its mass and its number, atomic number. It essentially is a positive electron. So, alpha decay. What happens? A heavy nuclei decomposes and it produces an alpha particle. So now you have to figure out what is the missing other particle. So that's very simple. The arrow is your equal sign. You know that you have an atomic mass of 4 from your helium, so a little bit of algebra and you've solved for the other one. So you do that for the bottom as well. Because mass and atomic number are conserved. And so then, 93, not 92. You find element number 93 on the periodic table. So, spontaneous fission. Well, that would be if a large nucleus splits into 2 smaller ones. So, I am making up an example here, so this might not be something that really can occur. Okay, 95. So that could split into the elements that have mass of 45 and 50, about the same size. Okay? To do one of these, you'd be given more information so that you're not guessing like I am here, but I'm just giving you an idea. Usually, you're given one product and then you find the other. In which case, it doesn't matter whether one of your products is an alpha particle or a larger atom. Okay, so beta decay. That means you make a beta particle. Okay, now notice in your alpha decay that your mass number changes. Okay, 241 to 237. And your number of protons change. Okay, now look in beta decay. Your mass number remains constant because you have 18 equals 0 plus x. So we're still going to have a mass of 18. But now if we look at our bottom numbers, you've got a negative 1. Okay? So essentially what happened was a neutron turned into a proton by emitting a beta particle. And so we look on the periodic table, and that is fluorine. Now, if we have gamma emission, that usually goes along with that because remember, gamma is just electromagnetic radiation, so we can't put it in an equation and balance it. Now, if we have positron emission, where a positron was same mass as an electron, but positive. So now we have 241 still as our mass, and 95, because 96 equals 1 plus y to give us our bottom number. That should say plus, not times there. And so that is AM. So in this time, it was the opposite. We have a proton converting into a neutron. Now we could have electron capture. So notice we have 2 on the reactant side. So we would have 201, 79, and 79 is gold. Okay? So an inner electron was captured by the nucleus. Now, these are all just examples. In reality, we very often get a decay series with several reactions before you get a stable nucleus.